Okay, today we are going to talk about chapter 4, fluid kinematic. Till I hope we can finish till end of control volume and system representation, which is chapter 4.3 and section 3 of chapter 4. But before that, we have to talk about continuum hypothesis, and also we need to solve a question about the streamlines. So first, excuse me. Okay, so first I need to talk about the continuum hypothesis. All the things that we are going to talk about during this chapter needs to be applied, all the equation of motions based on the continuum or hypothesis. If not, you cannot apply it. Okay, so at first, let me okay. Second, please. Okay, so first, the definition. Okay, what is the definition of continuity as a word? Continuity means not interrupted, not broken, unbroken, consistent existence. But scientifically, in fluid mechanics, we are studying the behavior of very small pack of fluid molecules rather than individual molecules. We talk about that in chapters 1, that what does it mean? It means that we are not talking about the velocity of a single molecule. We are talking about a pack of molecules or fluid particle. This pack is a fluid particle that contains a lot of molecules. So the molecules may have different pressure, different velocity or movement direction, but an average, these are one set. This set has a single parameter on average, like temperature, pressure, velocity, that assigned to the center of that pack, right? So again, let's come back here, the meaning of continuity. We told you that we need to assume the flow is continuous, but at the same time, we assume that it has a bunch of the fluid particles. How is it possible to assume that when you are already broken it to pack of molecules? So at first, to describe the flow of a fluid, we have to describe it in terms of motion of the particles. So assign, if you consider that this pack of molecules is a solid part, then you can apply the velocity, acceleration, and everything, or like a motion of a solid body or rigid body motion. And move all the equations all the formulas like Newton's law, first, second, and third laws, all can apply it on this particle, okay? So here is the question again. If you break it down, how do you still assume the fluid is continuous or unbroken? So this is the answer. By assuming that the fluid particles are very small and tightly packed together. So that's still not very good understanding. It's not giving you clear understanding, okay? So I will give you an example. I'll give you an example here that is a simple plot in MATLAB, okay? Assume that you are going to apply, ask MATLAB to plot a function like y equal to x squared, okay? And you give a limit, and you know that you have to apply and give it the MATLAB the step size, right? So how does it work, and how the MATLAB plots that for you? First, it ask you to give the limits and break it down to x's, right? For example, -1 based on the step size jump, start from the lower limit, jumps and plus a step size or increment, then find the second point and third point and moving to the last, right? And for each point, you calculate what is the y. Okay, perfect. So when find those points, it give you the points on a plane, and finally connected those with a line. I mean the linear line, right? That's it. That's whole thing that is happening. So for example, here is your plot, okay? So I plot that here with the subsize of half. So -1, -half, 0, half, and 1 are the points, okay? These are your points. And then this is your function. So let's calculate y's, okay? Y is going to be 1, because -1 to the power of 2, and then the rest of the points. Then I put the points here, is 5 points, and connected those with the line, right? But you know that the y equal to x squared has a smooth shape. What is like broken here, correct? If you compare with the plot that you can find whenever or in the physics, you know that the plots of y equal to x squared is smooth, right? It's a curve and a smooth. But how you can fix it in MATLAB? Because MATLAB, again, just plot this one for you, cannot plot that. You are human, but MATLAB is a code, right? Cannot do that. So how can have a better shape of it? By describing the x's with more points or decreasing the subsize. So now I change the subsize here from half to 1/4 or 0.25. So more points I have here, and you can see visually these two and these 2 points are added. We maybe cannot see it here. This is red, and these two are red. It's not maybe shown great in the video, but if you see the notes in the Eulerian, you will see that the colors are different. Okay, so you have 4 additional points here. Again, with the linear line, you can see that it has a more perfect shape, right? Compared with the curve. So more smooth of plot. So as a result, all depends to the size of the step, okay? And how close these points are. If you add 1 or 2 more points here, and here, 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 again, you have better shape, okay? That's all. It's broken, but based on your assumption, it can give you better results, okay? That's how the pack of molecules or fluid particles work. So again, let's come back to the first point. How we can say that it's not broken? By assuming that the fluid particles are very small or infinitesimal and tightly packed, right? If you assume that these are the pack, we need to assume this. And also in all your equation of motion, we have this pack and all these packs together, and the effect of these pack of molecules or fluid particles on each other. So everything is based on the pack. You give them length and the size. So you give them the size because you have to, and you cannot apply this equation based on all molecules, right? You cannot apply that or in the molecule size. You have to be in much bigger size, right? And it's a pack of molecules. And at the same time, you are broken the domain, right, into the pack or particles. But if you see that if I had that pack, so that's the case, you have to compromise between these. You need to have the pack because you don't want to apply it on the fluid molecules, right? At the same time, you want this pack to be small and tight. These should be tight together. So at the same time that you want to small of the size of that, you want to be has a lot of molecules, right? That's why the scale and size scale is one of the most important things in fluid mechanics. The size of the scale of the channel is, for example, in the pipe is the diameter of the channel or length characteristic is the diameter of that. For open channel is again the depth of the channel. For a ball is diameter of a sphere. These are the characteristic lengths, okay? And one of the other sizes are the pack of the size of this box. And another length scale is how close the molecules are, because the distance between molecules is going to be different in the gases, and based on the pressure that you have, based on the density, based on the fluid that you have, and also the temperature that you have, right? So all are depends to different temperature, pressure, the fluid type, and you want to decide that which size of this pad. You shouldn't decide that. You need to know that, am I doing correct or not? Okay, are these equations valid in this size or not? For example, if you apply the Navier equation or any equation in the fluid mechanics, in between the cells in a body, it's not valid. Because the cells and the size bit, the channel that you have there is around the micrometer or nanometer, okay? And also the size, the distance between the molecules of the blood that is your fluid domain, okay? The fluid that passes between those cells are in size of the nanometer. Then you cannot assume there is a pack of fluid or fluid particle there that contains lots of the molecules, and at the same time is very smaller than the channel size or characteristic length. That's the validity of the fluid equations of motion. Those should be valid based on the size or length of the system. So if I expand the example here, if we assume that the fluid particles are very small and tied together, then in a fluid flow channel, such as for example, it's a pipe. The fluid particles are like points. So these packs are points. These are not boxes. Yes, it is a box of fluid, is a pack of molecules, but this just exaggerated here to be very big, right? Here is exaggerated, but in a fluid is like dot. Okay, so I'm going to show you that how much is smaller compared with the diameter of it, okay? These fluid packs or particles have its own temperature, velocity, and pressure and other characteristics, right? Which is the average of over the molecules of temperature, pressure, and is averaged over the fluid pack of the pack of molecules. And at the same time, you have to know that the size of this cube is like delta X, delta Y, delta Z. Delta is very small amount of the size versus a huge channel that you have, okay? So another thing that we have in the fluid mechanics is the length scales. One is length scale is L, which is the size of cube. The second one is the shape characteristic length. For example, it's the diameter in pipe. It's an example. The size of your real size of your shape, and also the mean free path between the molecules. Mean free path means the distance between the molecules. So molecules are not in the same distance between each other. So some of those are more closer and they are sliding on each other. So that's the only thing that you can say is the mean average path that each molecule can move before hitting to another molecule, right? So these are also in size of nanoscale or less. That's it. But what you want to have when you are applying your equation of motion, that the pack of fluid, the size, which is the length size of this particle, is much, much bigger than the mean free path and also much, much smaller than the characteristic length. So compared with the length scale of the shape, it should be like a dot. But if you zoom in on the dot, you want to have a huge amount of lots of molecules inside of that. Why? Because the size of lambda should be smaller, much smaller than the characteristic length. Okay, that's the meaning of the continuity. So continuity means that the scale size are very small, and you can assume that there is not change between these two sides of the molecules, packs or particles. So you want that the lambda over LC, which is known as Knudsen number, is almost zero. If it's zero, means that yes, you can find an L here that is between these two, because these two are highly different. Lambda is much, 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 much smaller than LC. And then you can find a smaller L or fluid particle size that is between these two, and you can apply your equation of motion on it. Okay? So because I cannot hear you guys, if you have any question, you can chat. We'll see if you have. If not, I will continue. Okay. Perfect. So chapter 4, based on Dr. Battaglia's notes, these are the rest of that is just mathematics. Part of that is mathematics, but continuum hypothesis is the meaning behind that. That I think that is required to know before moving forward. And for me, it took my PhD to understand the meaning of continuum. When I started this chapter, when I was an undergraduate student, I couldn't understand the meaning of that till I started my PhD. So maybe it's not that much familiar for you. Maybe it's still confusing, but it's a start of that. You will understand it more and will be more familiar with that. Okay. So start chapter 4. You are going to find the equation of motions, velocity equation, and other characteristics based on the time and location, and then apply the equation of motion, find the acceleration and velocity. So based on these, or we can apply We can find the force and momentum, and then finally find the Navier equation in chapter 5. Okay, so at the start, we have to know that fluid is a continuum that we already described, and is a collection of particles. And the motion of a fluid can be described in terms of the velocity acceleration of the particle. So everything is based on the particle, okay? But again, there is a difference between the particle's velocity and particles acceleration and the fluid's acceleration. So do you remember that we said that the particles is lots of molecules, and we don't care about the movement of one molecule, right? We talk about the average movement. If you see from top view in a channel and you talk about the flow velocity, right? The flow streamlines, the flow velocity always, the velocity of the fluid is in the tangent direction of the streamline, right? So in a streamline or a flow, also, we don't care about the fluid particles movement. You're talking about the average, how the average of the particles moves, right? The same view that you have in the fluid particles versus the individual molecules, we have the same view on the larger scale with the channel size or the fluids movement and the particles. Because again, particles are very small dots. So they may have different velocity direction, but we are talking about the streamline. So when they are coming into the data streamline and that point, they will have the same velocity that is in the tangent direction and with this constant magnitude, right? So it's like highway, and again, I will give you this example before. So it's a highway, the cars are moving the 3 lines of that. So if you follow one of the cars, it has maybe change the directions, maybe use the exit, or change between the lines, right? But we don't care. The streamlines are single lines, straight lines over each lines of the highway. Why? Because any of these cars where they are changing their direction and coming to the another one, they have the same speed of the others, and they have the direction of straight, right? That's why we only care about the average. So the average, if you get a picture, they are moving all straight over the lines with the different velocities, okay? So at a given instant in time, any fluid property may be given as a function of fluid location, okay? So providing fluid parameters as a function of space is called the field representation. So field representation means that what is the exploring fluid representation? Field representation means that what is the parameter as a function of location and also the time, right? So this is when this is an example. This is plus velocity field. If I change this with pressure, then this would be a pressure field, right? So it should be noted here that it could be any parameter. Okay. Velocity field is velocity components in each direction, and also because it's a vector, right? If it's not a vector, then you only must, for example, pressure, you don't have a vector. The pressure would be pressure as a function of x, y, z, and t. That's it. And there is no ijk because there is not, the pressure is not a vector, right? But we are talking about velocity because it's the most important thing parameter in the fluid mechanics. It gives you the streamlines, it gives you the acceleration, and all comes from the velocity equation. If you don't have velocity field, or then you can say that the velocity would be 0 and the fluid is at rest. Yeah, everything's okay. Thank you. Okay. So in 3D space showing each particle is assumed to be point. As a point, then point means that it has a location, right? The location means X, Y, and Z. Okay, so I put zeros here because those are just a location. These are not the parameter that changes. So if you don't have any number on it or I before that, this means that this is the coordinate system. So X could be anything. What in a specific points, so these are 0, 1, 2. So X, I, or Y, I are a constant number because you have a specific location. So any point would be a specific location. And this field could be applied, could be a field representation of any parameter. Velocity is one of those. So it could be any parameter of a fluid is a function of location. For example, pressure field representation could be P of X, Y, Z, and time. Okay. So here, again, because velocity gives you the movement and equation of motion, we are talking about velocity much more. So let's assume that you have a fluid particle that moves from this point to this, right? So location of this particle is when you have to decide that where is your reference point. So that's the reference point. If that's your reference point, any vector from the reference point to the location of the object or particle is the position vector known as RA at time t. Why? Because when the delta t time pass, and we assume that this is exaggerated, again, this is exaggerated, that is huge difference, but delta t is very small. We are talking very small amount of delta t. So delta t is almost 0 or very small. Okay. And this is the position vector. Okay. So at the time t and t plus delta t, this comes here, and this is your new location, right? Which is our at plus delta t. And also it's a vector. So how much, I write it here, and a shape like this, how much distance is going to pass by the particle? It's going to be s, right? It's the length that pass or distance that pass by the particle. Okay. You have to know that the particles are moving and it has to move, and the location object here and here are different. If not, then the fluid is not moving. The fluid is at rest, and you're coming back to chapter 2. You don't have any motion. It has to move to have a motion and velocity, right? Okay, so velocity of that object vector is the derivative of the p and of that object itself versus time. And it would be u I plus vj. These are the components of velocity, and wk. So in x, y, and z, you have I, j, and k, right? So this is it. That's why this is j, this is I, and that's your k. Okay? It's easy, okay? Also, what is the magnitude of the velocity? If you want to find the magnitude of any vector, it means that you have to find the square root of the components squared and summation of. That's how you find the velocity magnitude. So, okay. Here is the object. And then you find that if you zoom out and see that is a point, then from this point to this point, you find the direction of movement, means a vector from the end of point of this vector to the end of this vector. This would be your movement direction, right? And it's the velocity direction. And you know that if you zoom out, this is going to be a point, and this point, this is your velocity direction, okay? And if you wait till the second point and find the second velocity point, this is going to be here, and maybe here, and maybe here, right? And now if you add these points together, then this would be your streamline. That's where you find the streamlines. First, find the location of the object, and then track it to find the next point, and then find the direction of movement of the object. From the RA function, you can find the velocity direction and also velocity components and velocity amount of velocity that gives you that how much is, what is the direction and how much is the velocity. Then with the more points, because again, the distance between these two are very small. With the more points, you have a streamline, okay? But is it true that if you get these points, you have the streamlines? You're tracking a particle, right? Its particle maybe is a car in a highway. Then it may change the line, right? Maybe you have another streamlines here. For example, the streamlines are like this. Here it's moved in this line and coming here. It actually changed the highway lines. But if you track it, you find this line. So this is not a streamline, but is a pathline. Pathline means that you can see here mentioned that this particle path. Pathline is a line that the function for that is passed by a single particle. So if you want to study a fluid, you have to have the path lines for all the particles and then average it over the particles to find what is the average velocity in a single point of the domain and connect those to find the streamlines. That's hard, right? Another way is that you can say that, okay, instead of moving with the particle, I will stay here in a single point, which is this point, as a based on the reference point. I will decide that what is my constant point, okay? Then wait to see that how the other particles are moved. So particle A comes this point, and I will get the velocity of that. Then wait for the second particle. Particle B comes in this point. When it passes the point, I will see and check that and measure that what is the velocity direction and what is the velocity magnitude. Then average it and find that, okay, at this point, I have average velocity in this thing, right? And then move to the second point. Wait in the second point to see that how the particles are coming, and each particle, what is the velocity of each particle, right? It's like a bridge on top of the highway, and you are standing there and looking at down a line of your highway, right? And wait, and different cars are coming, and you will get that what is the velocity of the car when I'm standing here passing this point of the highway, right? Maybe some of those are changing at the line exactly over the line or the point that you are watching them, or sometimes are the moving straight, right? You take the average. Another way to find that is you can drive a car by yourself in a highway, right? You can drive the car, be in the car, and then find if I am in this line at this point of the highway, what was my velocity and what is the direction of the movement. When I'm changing the line, it doesn't matter, the points are changed. So I will get this car, and when at the end of the highway, I will come out, then coming back, drive the car again, and now use different lines and different points, right? So I have the information from a driving car 1, driving car 2, driving car 3, and then average over the points if 2 driving cars have passing 1 point in the domain. So it's hard, as you see, it's hard. You have to drive different times. But also it's hard to find the bridge and standing on top of it and find the velocity of different cars over time in a specific location, right? So it's again based on the 2 viewpoints and 2 methods for studying the fluid mechanics. That's why the Lagrangian and the Eulerian method are. Eulerian methods is like you that standing on top of a bridge. A Lagrangian method is like you that are driving the car. Okay, so here is a chimney. Yeah, and that's smoke. Okay, and you want to find what is the temperature field. Okay, represent the temperature field in different locations. In Eulerian approach, so there are 2 approaches here. In Eulerian approach and Lagrangian approach, Lagrangian approach is like driving a car, right? So in a Lagrangian approach, you have to put your temperature measurement system on top of only one smoke point. It's a smoke dot. So this is your fluid particle, and take the temperature of that when it's moved from out of chimney to the space. In the Eulerian methods, you can decide that where is your reference point, or where is the point that you want to measure the temperature for that, and put your temperature sensor there, and take the temperature of the flow in a specific point, but over time. Okay, this is also taking the temperature when it moves over the space. So this is only the function of time, because times, the location of that is a function of time, but you're taking the temperature actually as a function of time, because this is like a chain. You are getting the temperature when the location of the particle changes, but the location of the particle is a function of time. So actually you have the temperature over time. Here, not only the time it matters in the Eulerian method, you also have the location. Absolute location is x0 and y0 here because it's a fixed location, but you need to have the second and third and the other locations. So in top view, you need temperatures in x0, y0, x1, y1, but all as a function of time, right? If you combine and merge all these functions, you have x and y as variables. So this is location and time. That's the difference between Eulerian method and Lagrangian. Okay, so two approaches in fluid mechanics. Okay, so one is if Eulerian method that uses the field concept. It's absolutely confusing. I cannot understand what does it mean, the field concept, right? So it means that you have a fixed location it's like a temperature point O, okay? Like a temperature sensor at point O, okay? Function of location and time. Again, it is at a specific location, but you're talking about the whole domain, right? So yes, if you want to find the temperature at this point, at point O, only at point O, X and Y are constant. It's not a function of this constants. But if you are getting that information for the whole domain, then you need to change your point O to O prime, O double prime, and X1, X2, Y1, Y2, and then different temperature get that. Then average or combine those and bring X, Y as a variable, then you have the field representation like any parameter as a function of location and time. Okay. If you choose to go for the second approach or Lagrangian approach, then you need a fixed particle. Okay. The fixed particle means to put temperature sensor, attach it to a particle or particle. Okay, that's particle. And is a function of time, right? But you shouldn't forget that this temperature is not only function of time, but is function of x that is function of time, y of the particle that is function of time, and z of the particle that is function of time. But since these are the variables in the middle that are only function of time, then you can say that yes, p is only function of. But again, location matters because it's moving. Okay. So till here, you found that what is the idea of Lagrangian method and Eulerian method. Okay. But that's the question. Why we have two approaches and why not just only one approach for all? Okay, it depends that what are you want to study. Sometimes you want the flow field, or sometimes you want to track particles, right? In the experimental fluid mechanics, you need to track particles. Then the path line of the particles, and also you only mark those particles and get this results of those marked particles. Then you need to somehow find uh, the field of the streamlines of the flow and in the whole points of the domain. Okay, that's why you need two approaches, because you can get the information for single particles, then somehow you have to expand it for understanding the field, right? The field representation of the velocity and pressure and other things, but with only single particle, right? That's why we still need the Lagrangian, but mostly we use Eulerian method in mathematics, okay? So in general, the fluid mechanics are unsteady or three-dimensional. Check time first. Okay, still have time. So in general, fluid mechanics are unsteady and three-dimensional, but we have simplification and assumptions in fluid mechanics. Perfect. So one assumption is to assume that is only on a 2D plane, right? 2D plane means that one velocity component, like in the z direction, are very smaller than the other two. So it means that your flow is 2D, okay? The other thing is to define or assume that the flow moves uniformly. Uniformly means that is 1D flow. Or also you can say that the velocity at the point does not vary with time or steady, right? Again, as you can see, when the fluid particles move, absolutely the velocity changes. Even though that is not changing over time, if you can say it's not changing over time, it at least changes the direction of the velocity, right? So it cannot say that it's not a function of time. But if the flow is steady, it means that nothing going to change over time. Then all these, the path line that a particle passes, because it should not change over time, then the path line that all particle pass and also the streamline are merged, and it could be one line and one equation. We'll talk about it later. And also we have great videos from MIT that is recorded maybe 50 years ago, but the experiments are great. I'm going to show you or give you the link to the video that is explaining the meaning of streamlines with experimental stuff. That's perfect. Okay, a reminder from the mathematics, when you have vector A and vector B, okay, and you want to find what's the cross correlation between these two, okay? By crossing these two vectors, it's going to be 0 if and only if the vector A is parallel with vector B. When these two are parallel, okay? So in the streamlines, we have a line like this, which is your streamline, okay? And in a single point, you have a velocity that is in the tangent direction. And what is these two? These are U and B. These are your velocity components, okay? And if that's your Y and X, then this is going to be your DL. That is the tangent to the line and is based on dx and dy. okay? And the angle is hit. So based on the angle, the tangent of the angle is opposite over the adjacent. So V over U, that's nu, but yeah, always say V. So V over U and dy over dx. So these two are equal, right? So if you get the tangent of the line, because you want to find dl, the direction, and also needs to find the magnitude or velocity magnitude, right? Then you have the vector with two things. First, the direction, and also with the amount. If you multiply that in each other, then you have the equation of streamline. So that's why we mentioned that what is dl, that this is only direction matters because it has dx and dy. And the tangent of this angle, it would be v over u equal to dy dx, okay? This is going to be give you a function of vu and x and y. So these two are parallel. That's why we find the cross of these two vectors. It should be zero, okay? So what will happen if you say that this is 2D? If this is 2D, then you don't have this, right? If you don't have these two, then you can say that, okay, u dx plus v dy equal to be 0, right? Also, you can write that, okay, dy over dx is u over y. This has negative sign, but doesn't matter. This actually, you need to do cross correlation, right? So for the crossing these two, you of two vectors, it's like I, j, k, dx, dy, dz, and also u, v, w. And you can say that, okay, these are zeros. So I times dxv minus, this is dxv. dxv is not simple multiplication. So dxv minus dyu equal to 0. Then you can say that, okay, I bring it here, and dy over dx is v over u. That was the difference between the multiplication and simple multiplication and cross of two vectors. Okay. So we have two more lines. One of those are stick lines and path line. The stick line is line that consists of the all particles in a flow that passes through a common point. Common point, it means fixed in location. That means Eulerian approach. You have a stick line as an Eulerian approach because you fix in time, in position, and then get the average of the particle velocity passes through it. Okay. It's more for laboratory things. It's a laboratory. Laboratory line. Then the path line is what? Line traced by a particle. It's obvious. The line traced by the particle is Lagrangian approach. Steady. If the flow is steady, the steadiness means that the path line, decline, and streamlines are all merged and could be in the same point. In the same, they are the same equation. So if you find the streamline, then you have the path line also the strict line. So I wrote the details, more details. I was just again explaining that in the notes, but it's not really matters here. Okay, so we're talking about the mathematics. So let's find the acceleration field. The acceleration field means that what is the a vector of a as a function of time, right? At first, you know that the derivative of velocity over time gives you the acceleration. Okay, so first let's know what is the velocity as a function of location and time. Okay, you find it. It's xa, right? The location of the particle. It's a Lagrangian method. So location of the particle as a function of time, and also time. That time also changes based on the movement of that object, right? So velocity, the acceleration could be defined by the total derivative, right? So from mathematics, I will give you this hint that when you want to find d over dx, derivative of a x of a function that is a function of another function as x, so it means that you need the chain, right? The chain rule, use the chain rule to find the derivative. Then this is going to be f of x, right? Times dg over dx, correct? So here also you see that to find the derivative of v, for t is easy. You're just getting the integration, derivation. But for the x and y and z, you need to find the derivative over x and dx over dt. That's the chain rule, right? And also applied for y and z. And then you can say that, okay, so I know what is dx over dt, because dxa over dt is going to be your component of velocity, is u. dy over dt is v, and dc over dt is w. Then you can rewrite the equation as rho v over rho t, that is the velocity versus time, derivative of velocity versus time, and components times velocity of derivative of velocity versus the direction, right? So this is going to be your final equation for velocity as a function of t. Okay, but still needs to be rewritten that and more work on it to find better equation. Okay, so what is the capital D over dt is the total derivative that we did, is the derivative versus time, right? But you see that you have two type of terms. One is the term with the derivative of time, and the other is multiplied the velocity component and versus x, y, and z. Okay, so it's the name. Another name for the material derivative is the total derivative or substantial derivative. Okay, and here you can have any parameter. Remember, any parameter could be here. Okay, but if you put it as a velocity here, then you will have acceleration. This term known as a local acceleration. If you have velocity here, then this is going to be a local acceleration. But total is local derivative. Local derivative means that it's based on the location, but versus time, right? But These three known as convective term or convective derivative. So this is rate change with time, but this one is rate change with space location, spatial derivation or location. So what we know about it, rate change with time, rate change with locations, right? And T is a part of it. Perfect. So it's like Lagrangian plus Eulerian. Combine these two to find the total derivative. That's why another name for that is total derivative, right? So Lagrangian approach and Eulerian approach totally gives you the acceleration. But mathematically, for the acceleration as a function of time, you have two components, ax, ay, az, and for each direction, you need to write the equation term here. From mathematics, I also have to mention here that the rho v or rho any of terms could be any parameter versus the derivative versus the time derivative plus UVW multiplied by the gradient, it gives you this part. So mathematically would be V dot gradient of any parameter, right? So if that's velocity and this is velocity, then in X direction, velocity component is U. So you replace this brackets or parentheses as a term of U. So you will have derivative of U versus time. And then you have velocity components, UVW, gradient, dot of the gradient. The gradient is rho U rho X, rho U rho Y, and rho U rho Z. So U times that is the derivative or is a dot product between these two vectors, right? So in the second part, what is changing here as a parenthesis is U. Why U? Because it's X direction. And here, instead of U changes V because it's Y direction. And W because it's Z direction. So when you get these AX, AY, EZ, you will put it here and you have vectors. So these are not vectors, right? Because these are all scalars. These are scalars. But if you bring it here, this would be your components of acceleration components, and then you have the acceleration field, right? Other thing that you have to know is this is the local acceleration terms, and these are convective acceleration terms. Okay, so local acceleration shows that represent that the effect of unsteadiness. Unsteadiness means that how much change versus time, right? Change of velocity in time. But convective acceleration is represent the function of the function of the change of velocity in changing the space. location, a spatial location, right? By movement of from point 1 to 2. Okay, so this is the other thing that is your convective acceleration. Okay, so I think I don't have time for yeah, it's 10.07. So I don't have time to start a question for you, but I put the answer and solution of that example, but I will talk about that later in the next session at the start of the class, and then move for the contour volume and Reynolds transport theorem before starting this part, chapter 4.3. I will talk about an example or at least one example or maybe 2 or 3 examples to know more about the streamlines, because these are the rest of that is just doing mathematics, and you need to make yourself familiar with that because you will have problem. I see that most of the students have problem with that, the mathematics, with doing integration, with doing derivative, and that's the part. Even if you know the fluid mechanics perfectly, you are not good if you are not good in mathematics. So physics and mathematics are combined, and you have to be familiar with the mathematics part as well. So I need to give you a bunch of examples to make yourself ready for the exam and also homework. Any question? Okay. So if you don't have any question, you can leave, and I'll put this video for today in Jubilance. You too. Bye-bye.
Thank you.